welcome to the 8th lecture in this course. So in this lecture we are going to look at Grosvenor basis and use it to do some elementary but basic computations. So throughout recall that R is a polynomial ring in n variables over a field K. And let I be an R ideal. Sorry, one more point. This is a monomial order on R. There is an underlying monomial order which, and we will always refer to initial ideal, etc. with respect to that. Okay. So a subset G inside I is called a Grosvenor basis of I. Okay. Again, this is with respect to the given order. If G is finite and the initial ideal of I is generated by the set in G where G is from this finite set. Okay. So it is a finite subset of the ideal whose initial terms generate the initial ideal of I. So such a thing is called a Grosvenor basis. So remark that every ideal has a fine Grosvenor basis. So has a Grosvenor basis. That is because initial ideal is finitely generated by some in G1, in G2, or up to some m elements. Then by Grosvenor basis we mean the set G1 through Gm. So every ideal has a Grosvenor basis. And what we want to prove is that a Grosvenor basis of an ideal is a generating set for the ideal. So it is a generating set. So after we prove that statement, how we can think about Grosvenor basis is it is a generating set whose initial terms generate the initial ideal also. So it is not just a generating set. So before we do that, we need to prove a small lemma which is reminiscent of the uniqueness of the remainder when we divide in the one variable case. So here is the lemma. Okay. Let I be an ideal and G, some G through Gm, a Grosvenor basis for I. Okay. Let F be inside R. Okay. Now we know from the division algorithm from the previous lecture that we can write F as some AIGI plus R. But we could possibly have written it in a different way also. The same GI, but the coefficients might be different, and also the remainder, the term R might be different. So suppose that these two, this and this, are two expressions such that that satisfy the conclusion of the division algorithm, conclusion of the theorem about the division algorithm. Okay. So what does that, let me just say instead of writing it. Okay. So here it means that R0 or no term of R is divisible by in Gi for any I. Similarly, R prime is 0 and no term of R prime is 0 or no term of R prime is divisible by in Gi for any I. So this is what the conclusion of the theorem was, that there is such an R. Okay. Then R equals R prime. Okay. There is no guarantee about the coefficients of the Gj. The Ai need not be equal to Ai prime, but the remainder is uniquely determined. But what we have to use in the proof that it is a Grosvenor basis. Okay. So we will see how it's done. Okay. Okay. So let's so proof. This is not very difficult at all. Okay. So note that 0 is Ai minus, so we just subtract one from the other and we would get Ai minus Ai prime times Gi plus R minus R prime. Okay. Now, okay, so these Gi's are from the Grosvenor basis of I. So this expression on the left, the first expression here is in the ideal, hence this is also in the ideal. Okay. Therefore, R minus R prime is in the ideal. Okay. What we want to show is that R minus R prime is 0. Okay. If R minus R prime is not 0, then there exists J such that the initial term of Gj divides the initial term of R minus R prime. Okay. Now, what is R minus R prime? I mean, what is the initial term of R minus R prime? Well, we consider, we write R as some polynomial with monomials and coefficients, and we're subtracting the similar expression for R prime. The initial term must have appeared either in R or in R prime. If you just take a difference of two polynomials, some monomial that didn't occur in R or in R prime would not suddenly show up in the difference. Okay. So the observation is that the initial term of R minus R prime is a term of R or of R prime. Not necessarily the initial term, because it is possible that R and R prime had the same initial term and the difference cancelled it. So, but however, whatever the non-zero, if this is non-zero, its initial term must have occurred either in R or in R prime, and hence in Gj divides some term of R or R prime. Hence, in Gj divides a term of R or of R prime, which is a contradiction. And the contradiction was with the assumption that if this is non-zero, hence R minus R equals R prime. Okay? So we did use that it is a Grosvenor basis here. So it's not true for arbitrary generating sets for I. Okay? So it's only true when we work with Grosvenor basis. Okay? So just one that's the, so this is the end of this lemma. Okay, so just okay, maybe one definition. Okay. Let I be an ideal and G a Grosvenor basis of I. Okay. Let F be in R. Okay. So now we know that if you apply the division algorithm to F and divide it by the elements of G, okay, the element R in R obtained from the division algorithm same notation as above. As in that theorem. Okay, is called the remainder of F, okay, and is denoted by remainder of F when we divide by G, okay, the set G. Okay, and this makes sense only when G is a Grosvenor basis of an ideal. Okay, so before we apply this theorem, this result for a first application of studying Grosvenor basis, I just want to make just one remark. Let's go back here. So in this definition or in the previous proposition, we took an ideal and then took a Grosvenor basis. But however, nowhere in the statement do we refer to the ideal itself. It is always some statement about G and F and so on. So we really do not have to take an ideal to start with. All that we have to say is if G is we do not need to know I in the above statements. Okay. What is required is the following property, that G is a subset of R such that G is a Grosvenor basis for the ideal it generates. G is a subset of R. It is of course going to generate some ideal. Okay. So all that we need is that G is a Grosvenor basis for the ideal it generates, and we don't need to know what that ideal is. And as we learn more about Grosvenor basis, or given some set of polynomials, how do you find a Grosvenor basis that it generates? When we study that algorithm later, we will see that this is a statement that can be checked without knowing what the ideal is. Okay? So just keep this in mind. Although I stated those things for ideal, that's because till then we had not really thought about the property of a subset as being a Grosvenor basis. It was always with respect to an ideal, but it is, we don't need to explicitly refer to the ideal all the time. So anyway, so here is what is called the ideal membership test. Maybe before I do that, let me, sorry, we did this in the last lecture, but let me just remind you. From the last lecture, this is the proof of Hilbert basis theorem. What we really proved is that if G is a subset in I such that in G, G inside G generates in I, then G generates I. This was our concrete proof of Hilbert basis theorem, that I has a finite generating set. So what is this? This is just saying G is a Grosvenor basis, right? So this is just, so this statement is just in the language that we have introduced today. So it just says G is a Grosvenor basis of I. Okay, so the Grosvenor basis, any Grosvenor basis of I is already a generating set for I, but it has the following useful property called ideal membership test. So let's learn that now. Proposition ideal membership test. Okay. Let I be an ideal and G inside I a Grosvenor basis for I. For I. Okay. Then let F be in R. Let F be an element of R. Okay. We want to test whether F is inside I or not. Then F is inside I if and only if the remainder of F when divided by G is 0. So this again, it works for, first of all, to make sense of remainder of when divided by G, G must be a Grosvenor basis. The remainder part, the R in the division algorithm at the end is unique when we work with a Grosvenor basis. So this is well defined, okay? And then we can ask this question, and okay? So this is what is called the ideal membership test, and this is one of the first applications, immediate applications of the theory of Grosvenor basis. Okay. Proof. Okay, so let's prove the if part. Remainder of F is 0 implies that there exists AI such that F is sum of AI Gi plus 0. This is the, remember, this is this thing, right? So it is 0. So in other words, therefore, F is inside I. Right? The Gi's are inside I, any linear combinations inside I, so F is inside I. Okay. So this is the easy part. Okay. One did not really use that it's a Grosvenor basis, okay, except to say that, yeah, this part is. Okay, so now let's prove the other direction. Okay, so let F be inside I. So by way of contradiction, assume that remainder, so maybe let's write R for the remainder. Let's assume that R is non-zero. Okay. So, but what is R? R is f minus some aigi. This is also inside I. I mean, this is inside I irrespective of whether it's 0 or not. Okay, 0 is also inside I. This is there. In other words, the initial term, so now is where it's non-zero is used. Initial term of R is inside I. Okay, which means that there exists a J such that initial term of Gj, there exists a G inside G such that initial term of G divides initial term of R. Okay. That's because it's a Grosvenor basis, since G is a Grosvenor basis. Okay, so this is true, but this was this is not how division algorithm would have. Okay, so this contradicts the conclusion of the division algorithm. I mean, sorry, whenever I say division algorithm, I mean the theorem in which we prove the algorithm. We didn't explicitly write down the algorithm ourselves. Conclusion of the division algorithm. Okay. So, and why did we get this conclusion? The contradiction. The contradiction was from this assumption that R is non-zero. In other words, yeah, this is what we wanted to prove. Okay. So, ideal membership test is one of the first applications one learns after one becomes familiar with Grosvenor basis. Okay. So let's just look at the stuff that we discussed in this lecture. Let's look at it in Macaulay. So here is how Grosvenor basis is calculated. So again, this is back in the same example that we were discussing in the last lecture. R is kxy, q adjoint xy, Lex order, and g1 is this polynomial xy minus 1, g2 is y square minus 1, and we just call I the ideal of. Then we ask Macaulay to compute the Grosvenor basis. So the command is gb, g equals gb of I. So it doesn't just give you the list of elements in the Grosvenor basis, it keeps track of some other extra structure. So it outputs what is called an element of an object of Grosvenor basis class, and there's some diagnostic message. So we will discuss what S pairs are, etc. are later. So anyway, there's some diagnostic messages that we can ignore for now. It returns to us an object of Grosvenor basis class. And if you want to actually know what is the Grosvenor basis, then we can ask gens gbi. So it says y square minus 1 and x minus y. So that x minus y is there in this ideal was not obvious by looking at this. I mean, we can calculate it, multiply this by x, then we'll get x minus 1, and the subtract will get x minus 1, then they'll get an x minus y. Okay. So this is so this is there, and it says this is a Grosvenor basis. Okay. So now let's look at some ideal membership test. Yeah. So the same f from last lecture, which was x square y plus y square x plus y square, and the symbol is percentage sign to reduce modulo a Grosvenor basis. So we can do it in two different ways. We can ask f reduce modulo g, then it will say this is the remainder, or we could just give an ideal and then we'll get this remainder. Okay. And in the exercises we will try to understand these things a little bit more. Okay. So this is the end of this lecture, and in the next one we will start looking at further applications in solving polynomial equations.